Hello, everyone. Welcome to another session of ExpoLab Blockchain Speaker Series. And today it also is going to be a computer science distinguished lecture series as well, too. So it is my great pleasure to have Tal, Rabin, and Fabrice joining us today. And Tal is a professor at UPenn and also was the head of research at Algorand Foundation. She's right now, I believe, only serving in the capacity of consultant, while Fabrice is a computer science, focusing in theoretical computer science and cryptography at Algorand Foundation. So a little bit about Tal. Interestingly, she was at IBM Research for 23 years. I was at IBM Research myself, and our offices were kind of close by, but we never really had a chance or the opportunity to meet while I was at IBM. So several years later, after we both left IBM, I have the opportunity to kind of chat with her. And same as Fabrice. Actually, Fabrice, as soon as I left IBM, I think he joined IBM. And then shortly after, he went to Algorand. So kind of an interesting history that happened at IBM Research. And the other thing that I wanted to kind of add is that Tal has been instrumental in cryptography, and her work has really changed the field. In fact, by Forbes, she's top 50 women in computer science, and Business Insider ranked her number 4 as top woman engineer. So it is with great pleasure to have you today. So please take it away.
Okay. Thank you very much for having me. It's exciting, this whole class that you're doing and the focus on, I see I didn't turn off my WhatsApp. 1 second, that's not good. The whole class is exciting, and devoting it to this topic is very interesting, and maybe I'll do something like this eventually at UPenn. I'll get some tips from you on what to do. Anyway, today we want to talk about the Algorand blockchain. The talk will be comprised of 2 parts. I'm going to first talk about more theoretical aspects and the design of the blockchain and so on. And then Fabrice will really talk about more technical issues, how things are done, how they're built, what we can do, and so on. So it'll cover this whole spectrum of things. I cannot read the chats while I'm talking, so if there's questions, somebody please tell me, or just unmute yourself and ask. I love an interactive class, that would be great. So first of all, I want to say, I know that this was supposed to be for a blockchain class, but then I was told that it was going to be also a distinguished lecture. So there are things that are not just for people who know blockchain, as most of you do, but a little bit more broad in some aspects. So first of all, blockchains, in fact, are, when people say blockchain or crypto, it's not clear exactly what they mean. And there are 2 major aspects that people talk about. One is the underlying technology of the blockchain. And the second aspect is the cryptocurrency. Most people in the world, of course, are extremely excited by the prospects of the cryptocurrency and making money and so on. But the truth is that the underlying blockchain technology is really what's exciting in these all these things, starting from Nakamoto's protocol with Bitcoin to the more advanced blockchains that we have now and the developing designs. The blockchain and the cryptocurrency that resides on top of it, in fact, cannot exist one without the other. The cryptocurrency, of course, needs the blockchain because that's sort of the memory that propagates where all the transactions have taken place. But in fact, in many, many instances, the cryptocurrency is what's driving the blockchain. And what do I mean by that? We need the money to incentivize people in some instances in order to extend the blockchain. I'll just speak a little bit more about the blockchain in a second of what it is, or it really is more meshed into the issue of holding tokens, how you build your blockchain. Now, first of all, what is a blockchain? A blockchain, the technology, is simply a distributed, secure, efficient creation of a ledger that's write-only, cannot be muted, and can be visible to everyone. This is what a blockchain is. It's no more than that. You can think about it as a bulletin board that people can come and write messages one after the other. And once they're on the bulletin board, they cannot be removed or deleted. So this is what the blockchain is. And some might say that it's the infrastructure of the future. I don't know, but definitely at this time, it looks like it's offering a lot of exciting applications. The most popular, of course, is the cryptocurrencies on top of it. And in this talk, I'm going to focus on the blockchain technology. And when I said that the two need each other, I had said that, for example, for Bitcoin, the cryptocurrency is used in order to incentivize people to extend the blockchain. But in Algorand, as I said here, it's used in particular, the extension of the blockchain is based on how much stake you have, of how many algos. Algos is the native currency of Algorand, of how many algos you hold. And that's going to be reflected in what we're going to discuss shortly, which is proof of stake. Okay, so first of all, I said that we have what is a blockchain. It's basically a database where you add records and you cannot delete them, and it's viewed by everyone. But we have databases. Why do we need a blockchain? But databases do not really offer all the functionalities that a blockchain offers. Let's say a database held by a bank with all the records of its clients. Who has access to the database? What kind of data can each person see? What are the access to the data? What can you remove? What you can archive, and so on. So that's first of all with respect to the usage of the database. But also, these databases have other issues. For example, it's a central location where if something happens to it, it's a single point of failure and all the data can be lost. It might be hard to access. If I'm a bank in New York, my branch is in New York, and somebody from India, I want to do some transaction in India, it's hard to access the database to get my information from New York. So databases really create a lot of issues and problems, and the blockchain really comes to try and mitigate these issues. Okay. So it's called the blockchain because, in fact, it's a good picture of actually what's happening with this data storage. You add one block of data after another block of data, after another block of data, and so on. And there is something connecting the current block to its previous blocks. It's different in different types of blockchains, but there's something going into history for these constructions. And the blockchain has very nice properties, that it's writable by all, it's readable by all, and it's tamper-proof for all. Nobody can change it. And these things, the fact that it has these properties that anybody can write to it and anybody can read it, really creates some trust in that data. And trust in data is very important, as we see locally here. Okay. So it offers a lot of things which I said were an issue with the databases. it offers immediate global access. So if all my bank's data is on the blockchain, the bank in India can immediately access my account and do whatever needs to be done. And it's also very cheap to do transactions and to share information because of the nature of the blockchain. And it has the properties that it's virtually impossible to break the system. Okay. And we can do many, many things with blockchain. The most common used example is supply chains, because there is some factory someplace that is preparing fabric, and then it ships it to a place where it's cut, and then it's shipped to a place where it's sewed, and then it's shipped to the US, and then it's distributed to stores. And all these things are very easy to execute on a blockchain because all the information is there, everybody can access it, and it's clear the propagation of the things on the supply chain. And you can do a lot more. Okay. So there is this myth, I don't know, everywhere Vitalik is being quoted of introducing the blockchain trilemma. And what is the blockchain trilemma? It tries to say, what are things that we would want from a blockchain? And whether we can achieve them all together. What are the things we want? We want security for the blockchain. The transactions cannot be tampered with or removed once they've been committed. Of course, removing a transaction is detrimental to the proper functioning of the blockchain. Let's say if it relates to a wallet. If I remove a transaction that I paid $100 and suddenly I have $100 more in my wallet, that's not proper behavior. So we want security. We want scalability, meaning that we want to be able to do, to post many transactions that would work for real world use. I forgot the numbers of how many transactions Visa does, but for example, Bitcoin cannot support the number of transactions that Visa needs to do per second. And decentralization is that it allows everybody to participate in the creation of the blockchain. And what Vitalik was quoted as saying is that you can achieve at most 2 out of the 3. And what Algorand set out to do is really to solve the trilemma and to offer all 3 things at the same time: security, decentralization, and scalability. So we'll go slowly and see how these things were offered. And what are the things that the Algorand blockchain is going to offer? There are many things here on the slide, but I'm going to mention a few of them. A very important property is that there's going to be no forking. There's going to be forking with very, very small probability. Unlike in other blockchains where you have proof of work, where there is forking, it could occur. In the Algorand algorithm, this will not happen. And we will touch later on the point where this happens. I had said on the previous slide that we want scalability, that we want many transactions. But if, in fact, there are 2 types of scalability that the Algorand solution is going to deal with. One is actually really having a high throughput of transactions. And we have a block certified every 5 seconds with 5,000 transactions. So it's about 1,000 transactions per second. And this is a very high throughput. Another thing that's important is when you're working in proof of stake, unlike in proof of work, there's also a question of how many parties are in the network. And you have to show that you can execute your design, even if many, many more parties join the system, even if you have billions of users, you still need to show that your algorithms will work fast enough to deliver the result and not harm anything in the performance of the network. And also, I said decentralization, and the idea here in Algorand is that it's true decentralization, that anybody can join the protocol and participate in consensus, as long as you own some algos. If you have algos, you can participate in consensus and contribute. And we also want it to be cost efficient. We provide very low transaction fees, that the computations that will be done in order to extend the blockchain will be minimal. And why do we want this? The issue currently with proof of work blockchains is that they're not green at all. They're very, very costly in how long it takes to create each next block. And this is something, my personal opinion is that it's not sustainable, that we will be moving away from this. Maybe Bitcoin will stay forever as a historical remnants, but blockchains that will actually be utilized will not be able to waste so much energy. So we need the computations to be very small. And there are more things on the slide. I'm going to move forward. Okay. So what was the general approach for generating new blocks? And this was the approach that was introduced by Nakamoto for Bitcoin. And in fact, is also deployed and utilized in Algorand. What is it? You have to win the right to add a new block. I put win in quotations. What does it mean? I don't know. We'll discuss shortly. Once you have won the right, you think you've won the right, what do you need to do? You need to provide a certificate that in fact you are a winner, okay? And you provide the certificate that you're a winner and the next block. Then the block is added to the chain. What is added, we'll discuss later also. But this is just a general approach of thinking of how blocks are added to the blockchain. And now we have to define what winning is. We need to define what a certificate is. The only thing you know what it means here is a block, right? That's something that has a lot of transactions on it. And we also need to discuss a little bit once we get to Algorand, what it means to add it to the blockchain. Okay, so the first generation of blockchains were proof of work. And they are have a high cost per transactions. They're very slow because they're very labor intensive. I had mentioned this before in respect to being green, but it's also an issue with respect if you do the calculation per transaction. That's a huge issue. And they lack speed and they don't have finality because I said that there might be a fork. So this was the first generation of blockchains, and I don't want to knock it. I think that Nakamoto had done our field a huge service and it really created a revolution. This is something amazing, Bitcoin, and all the things that have followed from it. And then there are proof of stake, a middle version before the pure proof of stake. And what do proof of stake algorithms do? They say your ability to add a block is going to be dependent on your stake. This is what it means. You have to prove that you have some stake, and according to that stake, you'll be given the right to add a block. However, when we say that they're delegated or bonded, what we mean is that there is some subset of parties that are going to be making the decisions. And me, if I'm a user that has some tokens in that cryptocurrency, I will delegate the right to some other party, to a small number of parties, 20 parties, I don't know. And there's also a need to lock your tokens in order to participate in this process of extending the blockchain. And then we come to Algorand, which is a pure proof of stake. And what it gives us that it's scalable and secure. It has a low cost per transactions, everything I said before. It's fast because we want the computations to be fast. It's by design. There's finality because you won't have a fork with almost probability of having a fork is negligible. And it's green. So it also gives us things that are very attractive in our current thinking about climate.
So if I may to kind of just interject here, is it possible to kind of maybe slightly extend this picture to include more traditional consensus, BFD, and how would that sort of relate, especially I think to the previous slide? I think that's a very telling slide. Where would the traditional BFD be in this picture? And also kind of putting into the sort of with a remark of this ideal of decentralization is that the correct example we see in the proof of work. At the end of the day, when you look at it realistically, we see 4 or 5 entities control the entire computational power. So it's probably less decentralized than the banking system from that perspective, because even the global banking system, if every country puts forth a central bank, there's a lot more entity involved in maintaining that ledger. And similar thing could then later be argued in terms of the at least the first generation of the proof of stake, in terms of, well, the idea, the relationship of the stake and decentralization. So again, there's also, if you have more stake, then the system becomes potentially less and less decentralized, versus kind of going back to the traditional BFD consensus. Every person gets 1 vote. So it is decentralized with that perspective that every person has 1 vote, and it's democratic from that perspective. Of course, somehow you need to generate identity. So there is another level of decentralization to be able to form this identity in order to do the voting. So I would really be interested to kind of see your perspective. How does that fit into this sort of extending this picture?
Okay, so first of all, I want to say that my memory is not that long. I hung up onto some points of what you said, but you can later ask me again the points that I don't talk about. So first of all, the interesting thing about the Algorand protocol is that in fact it is a regular Byzantine agreement protocol. So we will see this later. So basically it falls really into that bigger picture. Of course, and this is what Algorand comes to deal with, that you cannot run a consensus amongst all the parties participating in the system, because that would be ineffective. Any Byzantine agreement protocol is n square and cube, whatever. And when you're talking about billion of servers, you can't do it. So in fact, you have to do something much more sophisticated, which I will discuss. That was one point that you made. About the fact that the computation or the consensus is being done de facto by a small number of parties, I would say the following. For proof of work, I would think that it would be hard to move away from it, because the proof of work really calls for these farms of computing and really getting a lot of power together and being able to do it. And a little fish just can't swim in that pond. And proof of stake, whether pure or not, again, if you're really a big holder of tokens, then of course you'll be participating much more in the consensus, you'll be more powerful. But in some level, that's okay, because the interests are aligned in the right direction. If you own a lot of stake, you should be able to influence things more. In the proof of work, You know, it might be the case that those farms of people don't have any Bitcoins, right? They're farming, and then they sell it the minute that they get it, but they're just doing it for profit. And really, they do not care at all about the blockchain and the token running on top of it. So in proof of stake, there's a little bit more of alignment, not a little bit more, there is alignment between the interests of the provers and so on. And the hope really is that once, if a token is really successful, then of course, there'll be many, many people, and you will not have heavy hitters that are control 10% of the blockchain, that this will not be the case. Currently, of course, I would say even for Algorand, which is a pure proof of stake, we're on a journey to get there. We're still not there, but we're definitely striving towards it. And we're hoping that with time, it really will be that there'll be many parties that participate in the consensus. I don't know if I answered everything you asked.
No, I think you answered everything. It's just, so I like the sort of the alignment example that you also gave. The only thing I would say is that perhaps for the Bitcoin also, there is a bit of incentive, is because the success or the perception of the Bitcoin also kind of determines the value of reward. So there is a bit of an alignment, probably not as direct as in proof of stake, but there is also something there as well that may promote staying longer in the infrastructure.
I'm not arguing with that point.
Yeah,
I agree. Okay, Fabrice, do you want to add anything on this point, or you're good?
Yeah, no, I just wanted to add to continue on the fact that this PBFT algorithm, like this traditional algorithm, would not work for millions of users. Even if you had the ability to, for some reason, give identity to people, and that would not be a decentralization issue, you would, as I said, you would not be able to run this traditional consensus algorithm between a huge committee. Like the committee would be small, like EOS 21 nodes. And yes, and that's also the issue of this delegated proof of stake, where even if the stake itself is completely like spread out properly, then the only thing you can do is vote for a validator. And we know that not necessarily, at least in EOS, we seem to have the example that not necessarily people will vote for the things which are the best, best aligned with their goal, I would say. And the Algorand has solved this issue because anybody can participate. Like that's really what the Algorand proof of stake provides, is that it's completely scalable in the number of participants. So even if you have millions of users, they can all participate. And if the stake is somehow like completely uniformly distributed, which is like the ideal, I would say, then you really have like complete security that you cannot achieve because of technical reason with the other technology.
Okay, I'll continue. Okay, so how did Nakamoto's consensus proof of work? We have all these servers who want to reach consensus in order to extend the blockchain. We have the blockchain, currently has 3 blocks. And what happens is that a puzzle appears. How it appears doesn't matter. And then after some time, some party pops up and they say, I have, one second, I have this, oops, my pen is not working. Oops, that did not go as expected. Okay, I'm not gonna use the pen. Okay, it comes and says, okay, there I go. I have the solution to the puzzle. That's my proof that I won the right. The winning is to solve the puzzle. Here's my proof of the puzzle. Here's my block. And everybody extends the blockchain by this additional block. Okay? This is what happens in Bitcoin. There's a puzzle and the proof of winning is solving the puzzle. Okay? It takes time and work to solve this problem. And this is why it's called proof of work. What happens in the Algorand proof of work? Again, we have all our servers and we have our blockchain of 3 blocks. And now a party pops up. There was no puzzle before, but it comes and it says, I have a certificate. Who gave them this certificate? Who knows? But I have a certificate. I'm going to show to you how we actually get this certificate, which is fascinating. But the thing is, I come, I say I have a certificate. Here's the block. Okay? Now, in Algorand, the consensus is a little different. It's not that you take this block and you immediately attach it to the blockchain, because we want to create this non-forking. For this, on top of it, we ask the question, do we like this block? Do we want to attach it? And then if the answer is yes, then it's attached to the rest of the blockchain. How do we answer this question? Do we like it? How we reach this decision of yes? We will discuss. Okay, but now I want to change the story a little bit, because it's not that we're working in this ideal environment where everything is great. We're somewhat working in an environment where there are adversarial parties, like that little guy standing there in the corner. And what he wants to do is he wants to impact the blocks, the transactions that go into the block. Maybe to starve someone, you know, never to allow any of Fabrice's transactions on the blockchain. It might have a strategy, we don't know what it is, but the guy is just not nice, okay? And he wants to harm the proper creation of the blockchain. So what happens is in this Nakamoto protocol, which is very interesting. In fact, you don't know who's working on the problem. The guy's just sitting there and he has no idea of who's working on this puzzle that appeared. So he can work on the puzzle himself, but that really takes a lot of work. He can't have a lot of impact if he's just solving the problem himself. What he would want to do is to corrupt the party that solved the puzzle and impact that party on what block it puts on. But the way that it happens, he's sitting basically in the dark and he doesn't know who's doing what. And then the minute that the server comes out and says, I solved the problem, here's my winning ticket for the win, and here's my block, it's already too late. The block is out there and the little guy can't do anything. So he can't get control on more blocks, and the blocks is attached to the blockchain. What happens in Algorand? You might say, same thing, right? They'll all sit in the dark and create their certificate, which is the case. So suddenly the guy pops up and says, here's my certificate. But then I said that we have to solve the question, do we like this block? And the way that we resolve it, Mo, to your question, is by running a Byzantine agreement. Maybe now this Byzantine agreement can be controlled by this little guy. Maybe if he likes the block, he can force the Byzantine agreement to say, yes, we like the block. And maybe if he doesn't like the block, he can force it away from the block. So we have an issue. But what will we do? We will utilize this technique that I said, that the guy is sitting quietly computing his certificate or computing his puzzle until he speaks out. And we'll say, each step of the Byzantine agreement, which we're going to be running, a Byzantine agreement, for those who don't know, is a protocol that brings parties to reach an agreement on some input. Each step of this Byzantine agreement will be carried out by a secret committee, and then it will announce its step and die out. Okay? So, first of all, I want to touch, and we'll get to this in a second, how we do this. So first of all, I want to touch on the question of how is the certificate created? And this is really the beauty of cryptography, that sometimes people design all kinds of primitives and people, what the hell are we going to be using it for? This thing has no use whatsoever. It might be very nice mathematically, but who knows what it's for? And this was the case with verifiable random functions when they came up. People really didn't know what they were going to be used for. But in fact, what they do is exactly create this type of certificate. I can create the certificate, I can compute it very efficiently, and everyone can verify that it's a valid certificate. I do my computation locally, and the verification can be done by everyone, that this is in fact a true certificate, which is amazing. The computation of the certificate is extremely fast. Contrast that to computing the puzzle in Bitcoin. Okay. So now we have to do this Byzantine agreement. And we have the huge set of people here on the left that you can see, this big set here. If we run the Byzantine agreement on this set, this is going to be terrible. It's going to be too expensive. It's not going to work. So really, we need to choose a small committee that will do the calculation of the Byzantine agreement. Okay? So we take a small committee. They're going to run this Byzantine agreement. And in fact, it's going to happen in a very interesting way. They're going to agree on this fifth block B5, and they're going to connect it to the blockchain. It's going to be connected to the blockchain. But the question is, how do we create the small committee when I said that the committee has to be secret, right? Because otherwise the little adversary, my little guy in the corner, is going to attack this committee and is going to influence its decisions. But we already have a technique for people to select themselves as winners. So how do we choose the committee? The same way as we did before. You choose yourself to say if you win the right now not to extend the blockchain, but to be in the committee. You present the certificate and you're allowed to do the calculation of this step of the Byzantine agreement, In fact, it's going to be much more than that. It's not just that you can participate in the Byzantine agreement. That's going to be too much. We do this thing, we repeat it for each step of the Byzantine agreement. And what we did what the Algorand protocol does is it has a super fast Byzantine agreement for a small set of people. It uses these verifiable random functions, and it uses this player replaceability. What's the player replaceability? That for each step, you choose a new committee to do the computation. And in fact, we now have follow-up work that enables us to compute any function. Here I only talked about Byzantine agreement, which in fact is also a simple case because parties don't have state. But we can compute any function, even if parties have state, in this model of player replaceability and this choice of small committees. And we call this model, you only speak once, YOSO, because that's exactly what I said. Every time someone speaks, they speak and they die. So we have a full new work doing it in general. So as I said, I have 6 more minutes and then I want to pass it on to Fabrice. The fact that we add the Byzantine agreement tack it onto the block suggestion, we disable this issue of the fork, which gives a huge advantage to the Algorand protocol. There's never a fork virtually. So, oh my God, that was terrible. Okay. So we wanted this protocol to have trivial computations, that it'd be really, really fast so that we can have this 5-second creation of a block. We want true decentralization because that anybody can join. And you see why anybody can join, because you join the big pool of people and then you're chosen into that little committee based on your stake, but anybody can be chosen and nobody can starve someone out. We have finality, we have scalability. As I said, even if there are more parties, we can do it. And also there's scalability in the sense that we can handle many, many transactions. And the protocols, of course, offer security based on their design. So here we have that the Algorand solution resolved the blockchain trilemma. We have securities because the committee members and every party, whoever takes an action, is unknown until after the fact. Everything is cryptographically signed. These things cannot be forged. We can get scalability for the two things. First of all, we can have a lot of transactions and we can work really, really fast because the lottery execution, which is the verifiable random function that I spoke about, is extremely fast and the committees are very small. So the computations happen over a small number of parties. And we have decentralization. There's a very low barrier to entry. You basically need to have tokens and then you can join. And anybody can participate in consensus. And so basically this solves the trilemma. And now I will pass it on to Fabrice.
Perhaps also maybe at this point, if any questions from the audience as well, it might be a good point as well too.
I have a question actually. Yeah. So couple of questions actually. So I believe Byzantine agreement is like a BFT protocol, same as PBFT and something like that, which is run between a set of committee members. So and when we run a Byzantine agreement protocol, I mean it will have some sort of guarantees like there can only be F malicious replicas of N and F is less than N by 3. Yes. So how do we ensure that when you generate these certificates, I mean the certificates are generated and the people who are part of the committees, that number is still less than N by 3? Because if they are too much, then yeah.
Okay, so first of all, I want to say, I forgot to say it because I think I clicked on the slide, something wasn't working there for me. In Algorand, you need, due to the proof that was provided, you need 80% of the money to be honest. Okay, that's one thing. Now, how do we guarantee that in the small committee, which is an excellent point that you make, how do we guarantee that the small committee does not have too many faulty parties? Of course, let's say if the adversary can corrupt 1 million parties and the committee is 1,000 parties, it can corrupt the whole committee. You have an issue. But this is exactly where this point comes in, that the adversary doesn't know who to corrupt. He can only corrupt people in some random fashion. And then a subset of 1,000 is going to get chosen into the committee through that certificate. You cannot forge a certificate and claim to be in the committee. That's not going to happen. So now the committee is going to have the same percent of good money in it. So the committee is going to have the property that it's going to be 80% good money. Excellent point. And if you want, in that Yosso paper, which is still not online, but in another related paper which we have, which is on ePrint, which is called Can a Blockchain Keep a Secret, or some variation of that name, we discussed these issues of why the committees follow the same probability of being malicious.
Somewhat, perhaps a follow-up question. What are the timing and the synchronization assumption here? Are we for both safety and liveness for that?
The protocol basically has a gossip mechanism, and there is some assumption that all messages are delivered. Now, I don't remember within how many seconds, but that amongst honest parties, you cannot cause this starvation, and through the gossip protocol, you will hear them within a certain amount of.
So there is a pulse, so everything needs to be sent in that pulse, whatever that.
Everybody has a local watch. Everybody has a local watch. They're not synchronized.
Yeah.
Okay.
Yeah, it's not, and I mean, security, like the no forking property holds whatever happens. Like if the adversary has full control over the network, you have security, like the adversary can delay the message as much as you want. For liveness, for the block to be created, there is some assumption about synchronicity, but as Tal said, it's not synchronous model. It's not a pulse. It's really local clock. And in addition, it's a very fast recovery. Like if you have a network partition, which means that some messages like between India and the US do not go, like it's completely separated in two. Obviously, it will automatically stop because it would fork otherwise. But as soon as the network partitions is resolved, like as soon as the messages are below, I don't know either the exact number, but the messages can circulate at a speed which is below blah blah between at least 95% of the parties. I mean, I don't have the number, but something like this. Then immediately the production of blocks starts again.
All right, I guess we can start the second part. Thank you so much.
Oh, hi, thanks Mo. So thanks Mo for inviting us. So Tal talked to you about a lot about the consensus protocol, which is like really like the foundation of any blockchain, and in particular of the Algorand blockchain. But nowadays, like most blockchain have a lot of features on top of this consensus protocol. And that's what I want to talk to you about in these slides. And I want to start by saying that what I like a lot about where Algorand is built is that it's really tried to be built layer by layer in a mindful way, and in a way that each new layer adds features, but do not remove any advantages, like do not spoil the lower layer. So let me go a bit more into it. So the first layer above the consensus protocol that Tal presented you is what we call layer 1 features, which include like layer 1 smart contract, Algorand standard asset, and atomic transfer. And essentially, all these features are somehow baked in the consensus protocol and benefits of all the advantages of the consensus protocol. So you have the same safety, exactly the same safety, same security. You have the same speed, like same throughput, same latency, and the same cost, like the same transaction fee. It's extremely cheap. So that's what this layer 1 feature property are. And obviously, there is a flip side. Like to achieve such great properties, we need to put some restrictions. So there are restrictions on expressiveness of the smart contract at layer 1. By the way, sorry, what I forgot to say two things. One thing is that don't hesitate to ask any question if you have any question at any point. And the second thing is, I don't read the slides, so just talk, or maybe raise your hand, maybe I will see that. And the second thing is, I will explain in more detail what smart contracts are if you don't know what these are, but here you can just think about like program executed by the blockchain. Okay. So as I said, layer 1 feature, very cheap, I mean, low transaction fee, high speed, high security, but some many restriction. And then, soon, it's not yet available, but soon we'll provide like a new set of feature, a new layer called layer 2 smart contracts, which essentially trade the transaction fee and the speed for more expressiveness. Like, so now you can write more easily smart contract, more complex smart contract, and so on. But obviously you will pay a little bit more, and the speed of the smart contract itself might be slightly slower, But very importantly, this new layer will not slow down the other layer. So by adding this new layer, this new layer 3 has been designed in such a way that it will not degrade the performances of normal transaction and layer 1 smart contract and so on. And this is not straightforward. Like if you think about Ethereum, essentially you can do any smart contract, but a smart contract which is slow will slow down everybody else. Like think about CryptoKitties that essentially like congested the full network 3 years ago. This is something we really want to avoid in Algorand, and I think we managed to do it using this novel idea.
So just a quick question. I mean, this is a very nice figure, and I mean, also a little bit, I guess the context is that our focus in my lab is we're looking at the BFT consensus protocol. So we're looking at traditional consensus protocol. And one thing is like, I think was mentioned earlier as well too, this certificate that we produce. Recently, I've been sort of thinking about this. Is this certificate as resilient as the Bitcoin certificate or the proof of work certificate? Because, for example, in PBFT, we could also generate these certificates. And these certificates could be, for example, the digital signature of everyone who voted it. But at some point, if all the sort of replica die and the single replica is standing and says, this is the proof, this is the chain, this is what the chain should look like, reconstruction of that certificate is cheap versus if I had developed that chain using Bitcoin, faking now a different chain, especially at a large length, is going to be much more difficult. So I just want to see with these verifiable function, verify random function, what would be the cost of generating? Can you go, I mean, I assume they kind of will be similar as to traditional BFT consensus in terms of the cost of generation. So somebody could just say, no, this was the chain, and you can't really refute it in those extreme conditions that more than, let's say in this case, more than 20% have failed or more than 30% have failed.
So when you mean certificate, you mean certificates for certifying, and I guess you don't mean certificate, the VRF certificate that I was talking about.
Well, no, that certificate itself, I mean, because essentially you're kind of proving I have the right to vote. I'm right now in that selected sample that was randomly generated. I have the right to vote. And well, and then that quorum, that sample quorum that gets generated on every round, they run the consensus, and I guess they produce this form of a certificate to show that this block is valid. And once they show that certificate, everybody else go ahead and add that block. In the traditional PBFT consensus, again, everybody vote, and once everybody gets agreed upon that vote, somehow a certificate gets created, for example, just collecting everybody else's vote. And unilaterally, you can decide whether this is a valid transaction or this is a valid block. You can go ahead and add it to my chain. So there is a form of a certificate that gets generated that gives the validity of that block.
Yeah, that's the same here. That's exactly the same here.
So is it fair to say, in general, then a block that is generated in a proof of work will be more resilient because the generation of a certificate there is much more harder. Here, after the fact, I can go ahead and sort of reconstruct the chain. I can go ahead and just rebuild all the certificate. I can recompute all those verifiable function. And if nobody was aware who were the participants at the time of those, the initial chain, nobody can really say anything. But in the proof of work, just because of the construction of every block is costly and it's a waste of resource, I totally agree with that. There is more resilience in the chain itself.
Oh, no, you cannot do that. Oh, I see. There is, like, actually, we can prove that if 80% at any point in time, 80% of people are honest and do not leak their secret key. Obviously, if you leak your secret key in the wild, you might have issues, but do not leak their secret key. Then there is no way. It's even stronger than proof of work. Like proof of work, it says, I cannot create a Bitcoin chain if I don't have enough power, and if I or if I have like I cannot create a Bitcoin chain if I don't have enough power, or like if I don't have enough time to do it. Here it's even stronger. Like it's impossible. It's just impossible. Like okay, you always need to say impossible, but like by impossible I mean cryptographically impossible. Like maybe Tal, do you want to give some details here or?
So I didn't understand exactly what the question was.
So the question in terms of the resiliency of the chain, the resiliency of the chain in a traditional PBFT consensus, people vote, they add block to the chain. And if every replica dies except one, let's say you have a single replica left, and somebody from outside says, what is the state of the database? This single replica can show this is the chain, and the best it can do, it can show the digital signature of every vote that was ever casted, and says, okay, this is all I have, and these are all the votes that was done. But the point is, in such environment with PBFT, is that, well, digital signature is cheap to imitate, and you could have reconstruct. That whole thing could have been pre-played by a faulty, by generation, many more public and private key, unless somehow you know the public keys of everybody who was involved. Somehow that information be preserved.
Okay, I got it. So the issue is the following. In the earlier stages that we have now, the situation is that in fact, most of the keys are held by parties that we know that are 100% honest, which is by the Inc., which is the company, and by the foundation. In order to be able to go back and to start and fork the blockchain, you really need to go back to a time where you have all the keys in order to do this. This is going to be impossible given if the blockchain is not worth anything. I mean, if the algo's gone down to nothing, then you can go and do it. But then who cares? But if the blockchain is still worth a lot, then to go back, you can't go back to the times where most of the keys were held by the Inc. and the foundation, because we are doing what's appropriate and erasing the keys and so on that signed for the specific consensus.
So yeah, I think. Oh, sorry, Tal.
So you can't go back in time. If this was your question, was this your question? Sort of this?
Yeah.
So you cannot go back in time because you cannot own all those keys, because those keys were in fact erased. However, at later times when the blockchain is much more decentralized, maybe everybody is bad. But that, by definition, if you're bad, you left the key, but if you were good, you erased it. So you can't go back and really get those keys.
Okay.
Yeah, what's happening here is that we are not using like the thing, like, okay, there is two parts. There is the election, but you can forget about the election. But there is then the signing, like signing that I propose this vote, the signing that I like this vote in the Byzantine agreement. And this signing key actually is what's called a forward secure signature. This means that actually we use a fresh key, a fresh public key for each round. And essentially, it's to simplify, but it's as if you have a fresh public key for each round, and you, when you register at the beginning, you say, I will be using this 1 million key for this following 1 million rounds. And each time you use a key, you erase it completely. If you are honest, like all the parties who are honest and we want the good of the blockchain, they will erase this key. So later, even if the party is completely corrupted, the key does not even exist. The secret key does not exist, and it's a signature, so it's impossible to recover the secret key. So it's impossible now to come back in. I mean, the only solution is to, at some point, the only solution to fork it is really at some point to get the secret key of 80% of the parties. But you need to do it at some point, everybody at the same time, like at the specific round. So it's extremely difficult. Like you cannot even like start saying, okay, I will try to corrupt 10% now, then 10% next month, and 10% in 2 months. It does not work because the keys, the 10% of last month are useless. I mean, you will not be able to fork if you do this kind of thing.
Okay, sounds good. Thank you.
Okay, yeah. So here, sorry. So back to the Algorand feature. So you have like this pyramid of layers, and I want to talk first about the layer one. So the one which is really baked in the consensus at some level. And the first thing in this layer is what we call Algorand standard assets. So as I told you about, I mean, for a consensus is always linked. I mean, at least decentralized blockchain is always linked to a cryptocurrency. So in our case, it's the algo. But sometimes you don't want to transact using the algo. Sometimes you want to use your own token. And that's what the Algorand standard asset provides you. It provides the ability for anyone to create a token like the algo on the Algorand blockchain. And you benefit from all the advantages of the Algorand blockchain. The same transaction fee as the algo, so it's completely negligible, like it's less than 1/10 of a cent. Same throughput, same latency. The only difference is obviously that these tokens are not used for consensus. They are not used in the Byzantine agreement, obviously. And the other difference is that you can have an optional administrator who can mint and burn units, freeze account, revoke asset, but it's optional, and all these features like can be activated and deactivated forever. If you know Ethereum, essentially it's similar to ERC20 and ERC721. The main difference is that, contrary to Ethereum, we don't need any smart contract for this purpose to create this token, this Algorand standard asset token. It's really baked in the consensus. In particular, this means that, okay, no code to write, that's good. And even better, you pay the same transaction fee as transaction with the algo, which is not the case for the ERC20 with Ethereum, where you would pay a higher fee to transact with ERC20 on Ethereum than with a normal Ether. And furthermore, it's like we have this website, and you can even do it very easily after the class if you want. You can create your own token. It's really just one click, and it's very easy, really, really simple to create your own token. So let's see a bit why would you want to create this token? And let's look at real world examples. And when I mean real world example here, I mean things that are deployed, used in production on the mainnet, and they are like really representing money. It's not like some test, it's not like proof of concept, it's really they're making money right now. The first class of assets or tokens that are interesting to use are what's called stablecoins. So you know that all the blockchain have their native cryptocurrency, Ether, Bitcoin, algos, and things like this, but in theory, you could use them to buy anything, to transact with a merchant, like this guy who bought a pizza for several Bitcoins a long time ago. But the issue with this token is that they are really highly volatile. So many people might not like paying with them. Like if in 5 minutes you lose 10%, it's not great to buy your pizza. So instead, what stablecoin offer is a way to represent like a normal fiat currency on the blockchain, like US dollar. It allows you to pay in US dollar equivalent over a blockchain. So you have all the advantages of a blockchain, including smart contract, we'll see later, something like this, and all the without the drawback of the associated cryptocurrencies, the volatility. So concretely, unlike here, I'm really simplifying a lot, and like I'm only talking about a very specific stablecoin, so it's not a stablecoin class. But let's talk about this specific stablecoin we have, like USDC and USDT. Essentially, you have a company who says, if you give me this token on Algorand, I will give you in your bank account the same amount of USD, US dollar. So this means that really this token is equivalent to a US dollar. Okay, so that's the first use case. Second use case is for rewards. Like if you want to reward your user for good behavior and you want to give them some tokens, like you know, these point cards in a retail store, for example. So here it's the same over the blockchain and on the internet. So we have two projects currently running at more than two, but two main projects. Like one is called Props, one is Planet Watch. So Props is really rewards for social content, and Planet Watch is reward for if you provide like good environmental data, then you get reward. Another use of Algorand standard assets is stocks and anything finance related, like shares of real estate and so on, that you can transact as token on the blockchain. So always, as usual, same advantage as before, like 1,000 transactions per second, less than 5 seconds to finalize, and so on. You can also use this to notarize documents and many, many more things. And as I told you, like it's really a real world thing. Like props, for example, has more than 2.5 million transactions per week. And that's really something you could only do with Algorand. Like if they try to do that on Ethereum, they would first like be 1/4 of the total number of transactions on Algorand. That would be ridiculous. And second, they would just go bankrupt because the fees would be too high because of Ethereum is still on the proof of work, and you need to pay all these miners who are spending a lot of electricity, a lot of money of electricity to mine Ether. So this is really something that Algorand provides compared to other blockchains like Ethereum. Okay, that was the first feature. The second feature I want to talk about is atomic transfer of group transaction. So let's suppose that Alice wants to buy 1 USDC from Bob. And let's suppose that she needs to pay 2 algo for that. So now you have 2 transactions. Like Alice needs to send 2 algo to Bob, and Bob needs to send back the 1 USDC. And whatever order you do these 2 transactions, you have an issue. Like the second one, the person who received like the second transaction essentially has the risk of not being paid. So if Alice starts, maybe Bob will not send back the 1 USDC and vice versa. And what atomic transfers do is that they allow to fix this situation, like to solve this issue. It allows essentially to say, I create a group of transactions, actually up to 16 transactions. And either all the transactions on this group succeed and they will be returned in the blockchain, or they all fail and we forget about them. But it's never the case that one succeeds and is returned and the other is not. Okay. A third feature I would like to talk to you about, which complements these 2 first features, is stateless smart contract, layer 1 stateless smart contract. So what is a stateless smart contract in Algorand? It's really something that allows to only to approve or reject transactions. Like normally, if an account corresponds to a user, I can have an Algorand account. And every time I do a transaction from my account, every time I send money, be it like USDC or be it algo from my account, I need to sign myself this transaction. Sometimes it's not convenient. And the stateless smart contract allows essentially to approve or reject transaction without signature, but according to some logic or to some program. And the program is written in some simple stack-based language that we call TIL. So it has a lot of restriction. It has no loop, a very strong restriction on size, on the number of complex operations like cryptographic operation you can do. But the flip side of this is that you have many advantages with this due to this restriction. One, it's easier to formally analyze and it's much less error prone than Solidity. And the second is that the price of it allows us to make the transaction fee with stateless smart contract as cheap as a normal transaction and with the same latency as the throughput. And furthermore, we anyway have like a slightly higher level like wrapper around it in Python to avoid having to always deal with a stack-based language if you don't like this. And finally, all of this stateless smart contract feature can be combined with all the things I talked to you about before, like atomic transfer and Algorand standard asset. And let's see actually an example which combines all these features. So remember, Bob wants to sell USDC. And many people may want to buy USDC from Bob. If you do it completely naively with atomic transfer as before, each time somebody wants to buy a USDC from Bob, Bob will need to sign the transaction. Because let's not forget that each row here in this diagram is really a transaction that is signed by the part which is on the left side of the opposite of the arrow side. There's the source side of the arrow. So you need to be signed to be authorized. And what stateless smart contract allows Bob to do is to not having to sign it, and instead just put on the blockchain this smart contract and say, now, anytime there is a group of two transactions, anytime there is such an atomic transfer, I sign it, and no need for my actual signature. So that's one application of all we have seen before, like stateless smart contracts, atomic transfer, and Algorand standard asset. Wait. Oh, okay. So okay, I don't have time to explain you to show you in detail how this stack-based work, but it does not matter. What's very interesting is that if you look at all of these features I talked to you about, you may think it's very simple. Actually, if you know about Bitcoin, stateless smart contracts are very similar to Bitcoin scripts. But the other property of the Algorand blockchain, namely the atomic transfer and the Algorand standard asset, makes stateless smart contracts extremely powerful. Because you can actually, even if you cannot store state in a stateless smart contract directly, you cannot store state directly, you can use a standard asset to represent some state. Like, for example, the number of USDC you have can be used in some way. And this is actually extremely expressive. We can even do a Dutch auction. So for people who like the coding puzzle, this is a very interesting thing you may want to think about, how to do a Dutch auction just with the free feature I talked to you about. But anyway, later, I mean, it's now deployed, but later we introduced a stateful smart contract, which simplify a lot the use of state. And what stateful smart contracts are, they are like, you can see them as application on the blockchain. It's kind of similar to Ethereum smart contract, but not completely, because, okay, I will explain later. But essentially what a stateful smart contract is, it's really just a program on the Algorand blockchain, which stores its state on the Algorand blockchain. And then you can call some function of this program, and it will modify the state. It's written in the same language as a stateless smart contract till, same restriction. And in addition, we have restriction on the storage of the state. Like the state needs to be constant size, essentially. Constant size, you have a constant size global state for all, I mean, globally accessible. And then you have constant size state per account that subscribe or opt into the smart contract. All of these restrictions are, again, for the same reason. We want to keep the same performance, and we want to keep the same fee for this layer 1 feature as for a normal basic algo transaction. And importantly, like, obviously, this stateful smart contract can be combined with everything we have seen before. And combining the stateful smart contract with stateless smart contract allows you essentially to create smart contract which also keeps funds, because like stateful smart contract are really applications that don't really keep funds, but if you combine them with stateless smart contracts, then you can keep funds. And actually you can construct quite a lot of applications. Like a lot of applications are possible just at this layer 1. For example, the simplest one is voting. Let's suppose that you want to vote on the blockchain. You can just create a simple application where in the global state you store the tally, like number how many votes you have for each person, let's say, and in each account you store for which person this account voted. So you see that constant state is sufficient for this voting application. Similarly, you can do crowdfunding. You know, like Kickstarter, you want people to be able to fund, to give money to a project, and only if there is enough money to reach some threshold, the project is funded. This means that if there is enough interest for the project is funded. Otherwise, everything is reimbursed for the user who provided the money. So that's possible, again, in this layer 1. More advanced, you have this algo swap, which is the equivalent of Uniswap. So I don't know if you've heard of Uniswap, but it's one of the biggest, largest smart contract on Ethereum. Like it's used by a lot of people, and it essentially allows to exchange the exchange in a decentralized way any pair of ERC20 token, in our case of Algorand standard asset token. And the price is determined by the liquidity provided by the user. Okay, forget it if you don't know what all this word means, but essentially, like, there is there is a way to dynamically compute the price. And we can do all of this in layer 1 stateful smart contract. So with all the advantage of the blockchain, all the scalability we talked about before. So yeah, so to conclude, like all this layer 1 feature, like that's sufficient for many applications. They have like same very low transaction fee, very low latency, same throughput as algo transaction. They are much more expressive than they may appear the first time. Like the first time I saw the stateless smart contract, I thought, we cannot do much with that. And then I thought about it, and then I thought, oh, actually, we can even do a Dutch auction. This is extremely powerful. But how expressive they are is still an open question, if you are interested. But anyway, sometimes it's not very convenient to write this smart contract because it's very low level. And that's where this layer 2 smart contract come into play. So they will trade like performance and cost for expressiveness. But importantly, they do it without slowing down any of the other features I talked to you about, without slowing down any layer 1 or any algo transaction. And so they can be used for contracts that are like too complex to write with layer 1, like even maybe they are possible to write, but it would be too painful, or they are too computationally demanding, like checking zero knowledge proof, like a ZK snap. And as I told you, the goal is really to allow such contracts while not slowing down the blockchain and while keeping the blockchain secure. And if you remember, like the layer 1, like the base consensus algorithm, like really work per block of 5,000 transactions, and every 5,000 transactions, every 5 seconds, you have one block which is added to the blockchain. And actually, like among these 5 seconds, maybe there is 200 milliseconds, something like this, which is allowed for the evaluation of all the layer 1 smart contract, of checking whether people have enough funds, like of updating the balance of all the accounts, because all the other time is actually used in to go sip the blocks and things like this. So you have very, very little time in this 5 seconds to do all the computation you want. So obviously, if you are trying to do like very complex smart contracts, and if you are doing like naively, like Ethereum does it, you will increase significantly the time to produce a block. And you will no more have this finality in 4.5 seconds. There is no way. And you may think, okay, there is no solution. There is no solution to your problem because I want to be able to make contract call, and I want speed on normal transaction. But at the end of the day, a contract call needs to be transcribed into a normal transaction. Like it needs to be registered on the blockchain. So there is, how do we do both of these things at the same time? And I think the very nice idea is that let's do the contract call, like evaluate the contract outside of the main chain, outside of the consensus. And it may take some time. Maybe it takes 15 seconds to evaluate the contract. That's fine. But when the evaluation is done, let's just like say, okay, my evaluation is done, and like add it to the blockchain. And now like the contract call are no more like blocking, like there are no more the bottleneck. And the very nice idea is that obviously you need to evaluate these contract calls correctly. Like you don't want random people to evaluate it and claim random thing. You want really that the contract, like the code is executed exactly as it should be executed. And another idea is that instead of having all the nodes evaluate this contract call, which is crazy, what we'll do is we'll create a committee, like select randomly a committee, the same way that we selected a committee for the consensus algorithm. Like remember what Tal showed to you, the picture with all these people, and like a small committee is chosen to vote on the block or like to agree on the block. Here we do the same thing. We select a small number of people, exactly the same way, to execute, to run the smart contract. And when they run it, after running them, they will sign the result, and then the result will be incorporated in the next available block. And you may say, okay, there is an issue here because the contract can take a long time, and maybe the blockchain state changed between the time I started running the contract and the time I'm ready to register the result. And the idea is that actually the contract execution committee is much smarter than that. It will not only sign the result, it will also sign the prerequisite. It will say, okay, update this value if the blockchain was in this state, and if the blockchain was not in this state, fail. And then there is a lot of things to figure out, like to ensure that one failure does not cause everybody else to fail. You need to be able to formally find the prerequisite and things like this. So lots of work, but that's really like this new idea of like running it outside and making it work, really like ensure to keep the same performance for normal transaction while adding this more expressive layer.
So in a sense, is it also, so what it's doing is that somehow it's taking the snapshot of the time that the contract was initiated, and if the snapshot hasn't changed, then it allows the contract to go through?
Yes, exactly. Exactly. And yeah, and then yes, exactly. There is a blog post for more detail. And okay, I want to quickly talk about actually about this point that we'll appear soon, is that blockchain are very interesting, but if they are alone, like it's unlikely that we'll have a single blockchain like dominating all of them. We need interoperability between the blockchain. And as Mo was mentioning it, actually, what I mean, you have like essentially what the blockchain provides is certificates for blocks or for transactions. The issue that the certificate of Algorand, I mean, in theory, you could have other blockchains with the certificate of other blockchains so that they can interact with each other. But the issue is that the certificate of Algorand is complex. Like it uses this fancy VRF, complex cryptographic tools. I mean, complex in the sense that's not for cryptographer, but for like, I mean, it's less known than signature at least. So the idea of this compact certificate is to allow to create a certificate which does not use all of these complex cryptographic tools. It's much simpler. It's using other ideas to construct this. And then now, when you have this compact certificate, you can make other blockchain like Ethereum understand Algorand blockchain. And now you can transfer assets between Algorand and Ethereum, for example. So that's work in progress. Like the layer 2, that's also work in progress. Okay, we'll really go very quickly here because it's late. What I wanted to say is that like now it's really targeted at developers, that we have lots of development tools. I mean, all the people that talk to you really liked how to develop on Algorand, especially compared to Ethereum. Even if we are younger, like we managed to like really get development tools that helps and really good documentation. And so here I'm giving you like some of the tools, but just wanted to highlight, for example, we have like a complete online tool to start, like create your token, your first smart contract. We have SDK for JavaScript, Python, Go, Java, C#, Rust, and so on. We have like plugin for different IDE and standard IDE. We have the equivalent of all the infrastructure you need. Like if you are familiar with Ethereum, you know that you need an API service. Like in Plura, we have the equivalent for free. You need a MetaMask wallet like MetaMask, we have the equivalent for free, and so on and so on. If you want to start building, really the best solution is to go on developer.algorand.org, maybe go to the getting started page. You have lots of tutorials. You can find whatever best way you like to learn, like learning by tutorial, by looking at the complex application, learning by step-by-step, like concept understanding. Like you have many ways of learning. People really like our documentation. I mean, I really got many people liking it, so it's not like just me saying that I like it. And I did not write most of it, so it's not my own praise. So anyway, everything is open source. If you have any question, we have a Discord server if you like synchronous communication. If you have like a Q&A like Stack Overflow. We now even have the office hour, very simple. You just pop in. If you have any specific question, you can also just contact me directly at Fabrice@Algorand.Foundation. And if you join the Algorand community, you can get many rewards. You can, as students, it's very easy to be an ambassador, like write article about it, more or less technical, write tutorial, like coding tutorial, programming tutorial. If you don't know even what to do, we have some bounties. Like you can get award by just check if there is something you like, and you can do it. We gave award if you develop a tool and application. You can, and if you are like ready to do a bigger project, we also offer grants and even accelerator. Like if you really have a startup idea, you are ready to go get apply for funding. We have accelerators that like help you like go from startup to I guess multinational. Yes. Okay. Thank you very much.
Thank you so much for this wonderful lecture. It was truly appreciated. So perhaps I think if there's other questions from the audience. So I guess I was kind of, my prediction was slightly correct. I guess we passed 6 o'clock too, just based on past experience. So let me just, I'm going to ask my last question because I think perhaps I wasn't really 100% clear on it. So and if it's too late for you, I don't want to hold you either. So just be honest on that. So traditional consensus, you do a voting round, and after the vote is done, if enough, if there is an honest replica remains, you can remember the result of that vote and you can show the result of that vote. And more specifically, if F+1 people are still stick around, you can say, okay, this is the result, and you can, if there's F+1 matching result, then you say, okay, then that was the result of the vote in the last round. And the other thing one can also do is, if I show a certificate saying that this is the result that I have, and the certificate of that result is all the votes that had collected it, and all those votes have been signed. There was a digital signature for the messages that was sent. And so if I can show the digital signature of how I reached this decision, essentially I can form a certificate. So a single individual can respond the result of this vote based on some form of a certificate. Now, if, let's say a very catastrophe case, nothing remains except one replica. And that replica wants to show prove what was the result of the last round. I can still go ahead and show this proof of certificate, but you can't really trust that, because unless I know exactly who were involved in the decision-making, those digital signature can be just reconstructed. I could just generate a new identity, create some signature and say this was the result of the vote. Unless somehow the membership information was ingrained somewhere. And the traditional consensus just basically doesn't provide that. But the one thing about the Bitcoin and the proof of work is, when I show you something, there was a work involved in creation of that. So faking it is prohibitively much more expensive than just creation of these certificates. And I was just kind of asking, where does the Algorand sit? I feel it's going to be similar to the similar to the traditional BFT, because it's essentially voting and signatures. But so that was the question that I had, because it seems to me, because we've been kind of looking at, it seems these proof of work are fundamentally more resilient in this situation. Of course, if you have enough replica remains, then you can get that resiliency. But in those extreme cases, maybe in practical setting, they tend to be more resilient, I think.
And I'm not sure. Sure, Fabrice, go ahead.
Yeah. I think the question is whether what remains. Like, if what remains is the list of public keys, like the list of actual identities and one replica, then you are good, because I mean, except if all these the secret keys are completely leaked for some reason. But let's suppose that the secret keys have been kept secret by the parties. The party just died, but they did not reveal their secret key. If you know exactly the list of public keys, you're good, because you can check the signature, and by the security of the signature, I'm sure that it's impossible for somebody else to create a signature for the same public.
But if you have that.
Yeah, so on Algorand, what we suppose is that the Genesis block is here. Is known. Like, so for Algorand, we suppose that the Genesis block is known. And in the Genesis block, you have the list of the initial people who are allowed to generate blocks, which is essentially the link of the foundation. But it's a two entity like running Algorand essentially. But so you are, if you have this block, then the full blockchain is uniquely defined as long as 80% of the people are honest at any round. That's what we can prove. But yes, that we suppose. We suppose that the Genesis block is never lost. Like everybody knows what the Genesis block of Algorand is. But then if every other replica disappear except one, and we have the Genesis block, then there is no way to create a new blockchain.
I see. Because I mean, we're kind of looking at this space. I think this is a very interesting space of the unification of the permissionless and permission, more particular BFT, proof of work, and proof of stake. I think kind of a generalization of those ideas to create a protocol that is more resilient, for the reason I kind of mentioned right now, and more performant on the PBFT side. I think that's a very interesting line of work. For example, just kind of give you also a number in terms of some of the work that we're doing right now with ResilientDB, our own fabric, is that we're hitting about scaling to 500 machines globally, so 15 countries, and our sort of peak throughput is about 1.2 million transactions per second. So I mean, 3 years of work getting there, but so of course we can't get into 1,000 machine or 1 million machine, but I mean 500 machines and still 1.2 million transaction. I think it's per second. So I think that's still, you can do a lot with a traditional BFT consensus, well, of course, with a lot of improvement. So that's kind of where we're sitting in terms of the research side.
Yeah, the Algorand, I mean, at some level, like it's a Byzantine agreement, so it's not PBFT, but it's another one, and it's done in committees of 1,000 people. Like the committee we said are 1,000 people, but it's fixed.
No.
Like even if you have 1 million, 1 billion user, we will only select 1,000 people. So then the performance is just what's the performance for 1,000 people in the blockchain, and essentially it has been tested. It's very close to, it's less than 5 seconds. So it's very impressive. But obviously we are just talking about 1,000 transactions per second. We can optimize to get more, but I don't think we can optimize to get 1 million transactions per second with this kind of protocol.
Yeah. All right. Again, thank you so much for this wonderful lecture. It was very insightful, and so I mean, on behalf of ExpoLab and UC Davis, I really want to take this opportunity and thank you.
Thank you for
having me. Thank you very much. Thank you. Thank you for inviting us.
Bye.
Thank you, everybody.
Bye.